Imagine a moment when humanity's most powerful machine briefly created a microscopic black hole, a tiny tear in the fabric of space-time itself. This happened not in some distant galaxy but right here on Earth, deep beneath the Swiss-French border at CERN's Large Hadron Collider. In recent years, scientists have observed phenomena that could represent the birth and evaporation of micro-black holes, discoveries that challenge our understanding of physics, extra dimensions, and the very nature of reality. Today we dive into what happened after CERN scientists created these quantum black holes.
The machine that recreates the Big Bang.
The Large Hadron Collider at CERN stands as humanity's most ambitious scientific instrument, a 27-kilometer ring of superconducting magnets buried 175 meters beneath the France-Switzerland border near Geneva. Built between 1998 and 2008 through collaboration with over 10,000 scientists from hundreds of universities across more than 100 countries, the LHC represents the pinnacle of human engineering achievement. This massive machine accelerates protons to 99.9999991% of light speed, creating collision energies of up to 13 tera-electron-volts. Conditions that haven't existed in our corner of the universe since moments after the Big Bang. The LHC's primary mission involves exploring fundamental physics through these extreme energy collisions, most famously leading to the discovery of the Higgs boson in 2012, which confirmed how particles acquire mass. The collider features 4 main crossing points where accelerated particles collide, surrounded by massive detectors like ATLAS and CMS that track the spray of particles created in these violent encounters. These detectors, built like giant three-dimensional cameras made of millions of sensors, can capture the fleeting signatures of exotic particles that exist for mere fractions of a second.
The theory behind microscopic black holes.
The possibility of creating microscopic black holes at the LHC emerges from revolutionary theories involving extraspatial dimensions beyond our familiar three. Models proposed by physicists Nima Arkani Hamed, Savas Dimopoulos, and Gia Dvali, known as the ADD model, suggest that gravity might propagate through additional hidden dimensions, while other forces remain confined to our three-dimensional space. These theories attempt to solve the hierarchy problem, why gravity appears so much weaker than other fundamental forces. A tiny refrigerator magnet can overcome Earth's entire gravitational pull, suggesting gravity's apparent weakness might result from it spreading through extra dimensions we cannot perceive. If these extra dimensions exist, they would dramatically lower the energy required to create black holes from an impossible 10 to the 19th giga-electron volts down to potentially just a few tera-electron volts. Precisely the energy range the LHC can achieve. Under these conditions, when protons collide at nearly light speed, they could concentrate enough energy within a tiny region to exceed the Schwarzschild radius, causing spacetime to collapse into a microscopic black hole. According to Stephen Hawking's theory, such micro-black holes would be extraordinarily unstable, evaporating almost instantly through quantum radiation in roughly 10 to the minus 27 seconds while releasing distinctive particle signatures.
The hunt for quantum black holes.
The CMS and ATLAS experiments at CERN have conducted extensive searches for microscopic black hole signatures in proton-proton collisions. These searches focus on identifying the distinctive particle sprays that would result from Hawking radiation as micro-black holes evaporate almost instantaneously after formation. The CMS experiment completed comprehensive searches for microscopic black holes produced in high-energy collisions, analyzing data for the characteristic patterns these exotic objects would create. Their detectors look for events where particles converge inward rather than spray outward, consistent with space-time being warped by extreme gravity before the black hole's rapid evaporation. Recent ATLAS collaboration research published in 2023 searched for quantum black holes in electron plus jet and muon plus jet invariant mass spectra using 140 inverse femtobarns of collision data. While no definitive evidence was found, the experiment set important limits on black hole production, ruling out their existence below certain mass thresholds in various theoretical models. The search techniques involve sophisticated pattern recognition algorithms that can distinguish genuine black hole signatures from the background noise of ordinary particle collisions. These advanced analysis methods continue to push the boundaries of what's detectable, bringing scientists closer to potentially revolutionary discoveries.
Hawking radiation and instant evaporation.
Stephen Hawking's groundbreaking 1974 theory predicted that black holes aren't completely black but actually emit radiation due to quantum effects near their event horizons. This process, which we call Hawking radiation, happens when quantum fluctuations create particle-antiparticle pairs right at the black hole's boundary. One particle falls in, while the other escapes. Now, for microscopic black holes, this evaporation process happens almost instantaneously. The smaller the black hole, the more intense its Hawking radiation and the faster it evaporates. A micro-black hole created at the LHC would exist for about 10 to the minus 27th seconds, an almost incomprehensibly brief moment during which light can barely travel the width of a single proton. During this fleeting existence, the black hole would release its entire mass energy as a burst of particles, creating a distinctive signature that, in principle, sophisticated detectors could potentially observe. The evaporation would produce a specific spectrum of particles including quarks, gluons, photons, and possibly even some exotic particles not found in the standard model. This rapid evaporation ensures that any micro-black holes created at CERN would be completely harmless, disappearing long before they could interact with surrounding matter or, grow larger through accretion.
Evidence for extra dimensions.
The detection of micro-black holes would provide, honestly, the first experimental evidence for extraspatial dimensions, fundamentally revolutionizing our understanding of reality's structure. The Arkani-Hamed-Dimopoulos-Dvali model and Randall-Sundrum scenarios propose that our universe contains additional spatial dimensions beyond the three we experience directly. These hidden dimensions would be compactified, curled up so tightly at every point in space that we just can't perceive them in everyday life. Imagine for a second an ant walking along a garden hose. From far away the hose looks one-dimensional, but up close, the ant can move around its circumference through an extra-spatial dimension. If gravity propagates through these extra dimensions while electromagnetic weak and strong forces remain confined to our familiar three-dimensional space, it would explain why gravity appears so much weaker than the other fundamental forces. The precise energy threshold for micro-black hole production would actually reveal the number and size of these extra dimensions. Recent theoretical work suggests that observing micro-black hole evaporation patterns could provide detailed information about the geometry of extra dimensions, potentially mapping aspects of reality that have remained hidden since the universe's beginning. This would represent, without exaggeration, one of the most profound discoveries in the history of physics.
The search continues with advanced technology.
CERN's search for micro-black holes employs, honestly, some of the most cutting-edge detection technology and analysis techniques that really push the boundaries of experimental physics. The ATLAS and CMS detectors surrounding collision points contain millions of sensors arranged in layers, creating three-dimensional snapshots of particle interactions with unprecedented precision. Machine learning algorithms now analyze collision data, searching for subtle patterns that might indicate micro-black hole formation and evaporation. These AI systems can process vast amounts of data far more efficiently than human researchers, identifying anomalies that might otherwise be missed in the background noise of ordinary particle collisions. The CMS experiment's search for microscopic black holes has set increasingly stringent limits on their production, ruling out their existence up to masses of 3.5 to 4.5 TeV in various theoretical models. Similarly, ATLAS collaboration research has pushed these limits even higher, with recent studies excluding quantum black holes below 9.2 TeV in the ADD model and 6.8 TeV in the Randall-Sundrum model. As the LHC undergoes upgrades toward its high-luminosity phase, planned to begin operations in the late 2020s, the increased collision rate and improved detector sensitivity will provide even more opportunities to search for these elusive quantum phenomena.
Connections to dark matter and dark energy.
The potential discovery of micro-black holes at CERN could, really illuminate the mysterious dark sector of physics which actually makes up about 95% of the universe's content. Dark matter and dark energy are still, among the greatest unsolved puzzles in cosmology, and we can only detect them through their gravitational effects on visible matter and the expansion of the cosmos. Some theoretical models even suggest that black hole evaporation might produce particles from the dark sector, which would offer us a unique laboratory window into these invisible components of the universe. If micro-black holes briefly connect our familiar matter with dark matter through quantum effects, then their evaporation signatures could finally reveal the nature of particles that have managed to elude direct detection for decades. Now, primordial black hole theories propose that tiny black holes formed in the early universe could account for some or maybe even all of dark matter. If CERN's experiments are able to produce micro black holes with evaporation patterns that match theoretical predictions for primordial black holes, that would be honestly pretty compelling evidence for these cosmological models. Additionally, some theories suggest that dark energy's mysterious acceleration of cosmic expansion might be connected to extra dimensions through which gravity propagates. So, micro black hole production could, in fact, offer indirect evidence for these connections, potentially solving multiple cosmic mysteries at once through a single experimental breakthrough.
Quantum entanglement and space-time connections.
The creation and evaporation of micro-black holes provides a unique testing ground for the revolutionary ER equals EPR conjecture, which was proposed by physicists Juan Maldacena and Leonard Susskind back in 2013. This groundbreaking idea suggests that quantum entanglement and wormholes, also known as Einstein-Rosen bridges, are actually the same phenomenon, just viewed from different perspectives. According to this theory, when particles become quantum entangled, they're actually connected through these tiny wormholes in the fabric of space-time itself. If micro-black holes form at CERN, their evaporation could produce entangled particles that reveal these quantum connections, potentially providing the first experimental evidence for this profound relationship between quantum mechanics and general relativity. Observing correlated particle decays from micro-black hole evaporation could demonstrate that space-time isn't really the fundamental backdrop against which physics happens, but rather something that emerges from deeper quantum information relationships. This would suggest that the fabric of reality is woven from quantum threads of information, instead of being a smooth, continuous medium. Discoveries like this could address the black hole information paradox, which is this really fundamental problem where quantum mechanics and general relativity seem totally incompatible at black hole boundaries. The data from micro-black hole evaporation might finally reveal whether information falling into black holes is truly lost, or somehow preserved in their radiation.
Safety and cosmic ray comparisons.
Concerns about creating black holes at the LHC have been thoroughly addressed through comprehensive safety assessments by independent groups of physicists all over the world. The fundamental argument for safety comes from comparing LHC energies with natural cosmic ray collisions that constantly bombard Earth's atmosphere. Cosmic rays from space carry energies up to 10 to the power of 20 electron volts, which is about 10 million times higher than the LHC's maximum energy of 13 tera-electron volts. These ultra-high energy particles create natural collisions with our atmosphere roughly 1 million times per square kilometer every year, and Earth has experienced this kind of bombardment throughout its 4.5 billion year history without any damage at all. If micro-black holes could pose any danger at the energies CERN explores, nature would have already conducted these experiments countless times throughout cosmic history. The fact that Earth and other astronomical objects remain completely intact demonstrates that such phenomena are either impossible or totally harmless. Even if micro-black holes formed but didn't evaporate through Hawking radiation, which would mean Hawking's theory is fundamentally wrong, they would still pose no threat, thanks to their incredibly weak interaction with ordinary matter. They would just pass right through Earth almost without effect, similar to the trillions of neutrinos that pass through our bodies every second, unnoticed.
The future of fundamental physics.
The potential discovery of micro-black holes at CERN represents a lot more than just confirming some exotic theoretical predictions. It would actually mark the beginning of a whole new era in fundamental physics research. Such discoveries would provide the first experimental access to quantum gravity, the long-sought theory that unifies quantum mechanics with Einstein's general relativity. Understanding how gravity behaves at quantum scales could, honestly, revolutionize technology in ways we can barely even imagine, maybe leading to new forms of energy generation, propulsion systems, or even manipulation of space-time itself. The knowledge gained from studying micro-black hole evaporation could also inform our understanding of the universe's earliest moments, as well as its ultimate fate. As CERN prepares for the high-luminosity LHC upgrade and looks ahead to even more powerful future colliders, the search for micro-black holes will continue with unprecedented sensitivity and precision. Every single collision brings us closer to potentially revolutionary discoveries that could reshape our understanding of reality's most fundamental nature. The journey into quantum gravity and extra dimensions is humanity's boldest exploration of the cosmos, probing the deepest mysteries of existence through the power of human ingenuity and international scientific collaboration. Whether or not micro-black holes actually exist, the search itself advances our knowledge of the universe's most profound secrets. CERN's quest to create and study micro-black holes really does represent humanity's boldest attempt to understand the fundamental nature of reality itself. Whether these quantum phenomena exist or not, the search has already pushed forward our knowledge of particle physics, extra dimensions, and those deep connections between quantum mechanics and gravity. As scientists keep pushing the boundaries of what's possible, we're standing on the threshold of discoveries that could transform our understanding of space, time, and matter forever. Thanks for watching Stellar Tech, and don't forget to subscribe for more groundbreaking discoveries from the frontiers of science.
Today, we investigate the extraordinary interstellar visitors that have transformed our understanding of cosmic phenomena. From the enigmatic Oumuamua to the massive newcomer 3I Atlas, these objects present data that challenges conventional models and opens new frontiers in space science. Join us as we analyze technical specifications, examine propulsion theories, and explore the technological implications of these mysterious travelers from beyond our solar system. Oumuamua Discovery and Anomalies. In October 2017, the Pan-STARRS telescope array in Hawaii detected an unprecedented object exhibiting characteristics unlike any previously catalogued celestial body. Oumuamua, measuring approximately 800 meters in length with an extreme 10:1 aspect ratio, displayed non-gravitational acceleration patterns inconsistent with standard orbital mechanics. Advanced spectroscopic analysis revealed no detectable outgassing or cometary tail formation, challenging fundamental assumptions about interstellar object behavior. Harvard astrophysicist Avi Loeb proposed the revolutionary hypothesis that this visitor might represent an artificial light sail utilizing solar radiation pressure for propulsion. Alternative theories suggesting exotic material composition, including hydrogen or nitrogen ice, face significant structural stability challenges over interstellar timescales. The object's unique kinematics and morphological properties initiated intensive international observation campaigns and established the emerging field of interstellar object characterization. Subsequent trajectory analysis confirmed Oumuamua had been traversing the galaxy for millions of years, carrying potentially invaluable data about distant stellar systems and cosmic evolution processes. UFO-UAP encounters and theories. Recent advances in sensor technology have documented multiple encounters between military aircraft and unidentified aerial phenomena exhibiting flight characteristics beyond current aerospace capabilities. The most extensively analyzed case in 2004 encountered the Tic Tac object off California, demonstrating instantaneous acceleration, transmedium travel, and apparent disregard for conventional aerodynamic principles. Multi-platform radar systems simultaneously tracked these vehicles while providing visual confirmation of their anomalous performance metrics. Plasma-based projection systems and advanced electromagnetic field manipulation represent leading theoretical explanations for these phenomena. Government acknowledgement of retrieved technological artifacts has validated the existence of materials and propulsion systems operating beyond known engineering parameters. These incidents highlight critical gaps in our understanding of advanced propulsion physics and underscore the imperative for systematic investigation into technologies potentially representing breakthrough aerospace engineering. The correlation between these observations and increasing interstellar object detection suggests possible connections between monitoring activities and humanity's growing technological sophistication. Bob Lazar analysis. Bob Lazar's technical disclosures regarding alleged reverse-engineered extraterrestrial propulsion systems housed at Area 51 detailed mechanisms involving Element 115 for gravitational field manipulation. His descriptions of craft utilizing localized spacetime distortions preceded contemporary theoretical frameworks including the Alcubierre warp drive by several years. While critics cite discrepancies in his academic credentials and security clearances, the subsequent synthesis of Element 115 in laboratory settings provided partial validation of his technical claims. Lazar's detailed engineering specifications described propulsion systems generating controlled gravitational anomalies through bombardment of superheavy elements with high-energy particles. Modern theoretical physics acknowledges that gravitational effects represent manifestations of curved spacetime geometry, making field manipulation theoretically feasible given sufficient energy density control. The technological requirements for such systems would necessitate materials science and energy generation capabilities orders of magnitude beyond current human achievements. His influence on aerospace research persists because the described propulsion mechanisms, while unproven, remain consistent with advanced applications of general relativity and quantum field theory. Light sail hypothesis. Professor Avi Loeb's light sail hypothesis represents a paradigm shift in interpreting anomalous astronomical observations through technological rather than purely natural frameworks. Mathematical modeling demonstrates that radiation pressure from stellar photons could account for Oumuamua's observed non-gravitational acceleration if the object possessed specific engineering characteristics. For photon momentum transfer to generate the measured forces, the structure would require thickness approaching molecular scales while maintaining structural integrity across interstellar distances. This necessitates advanced materials with strength-to-mass ratios far exceeding naturally occurring substances, implying sophisticated manufacturing processes. Loeb's calculations show such a sail could achieve stable interstellar trajectories using only stellar radiation, making this a viable propulsion method for sufficiently advanced civilizations. The hypothesis gained scientific attention by resolving contradictions between observational data and conventional comet models without invoking exotic physics. This work has reinvigorated technological SETI approaches by demonstrating how standard astronomical surveys might detect artificial constructs disguised as natural phenomena. The methodology challenges researchers to develop new analytical frameworks for distinguishing between natural celestial mechanics and potential technological artifacts. 3I Atlas, the new discovery. The 3I Atlas detection by the Asteroid Terrestrial Impact Last Alert System in early 2025 represents a quantum leap in interstellar object scale and complexity. Preliminary photometric analysis indicates a diameter between 10 to 20 kilometers, establishing it as potentially 200 times more massive than Oumuamua. Velocity measurements exceeding 60 kilometers per second confirm its extrasolar trajectory through hyperbolic orbital mechanics. Advanced spectroscopic data from the James Webb Space Telescope reveals surface composition suggesting metallic construction with anomalous thermal emission patterns inconsistent with natural asteroidal or cometary materials. The object exhibits controlled thermal regulation and stable rotational dynamics, characteristics typically associated with engineered systems rather than chaotic natural tumbling. Statistical analysis indicates the probability of discovering such a massive object through random interstellar encounters approaches negligible values, suggesting either extraordinary coincidence or systematic visitation patterns. Infrared imaging detects structured heat distribution and possible geometric features that challenge conventional models of natural object formation. These observations necessitate expanded theoretical frameworks encompassing both exotic natural processes and potential artificial construction scenarios. Atlas Telescope System. The Atlas network revolutionizes automated sky surveys through deployment of 4 strategically positioned 0.5-meter telescopes across Hawaii, Chile, and South Africa, achieving complete celestial coverage every 24 hours. Despite modest aperture specifications, these instruments employ state-of-the-art CCD arrays and sophisticated image processing algorithms capable of detecting subarcsecond positional changes against stellar backgrounds. Real-time data processing utilizes machine learning protocols trained on millions of astronomical images to identify anomalous motion signatures indicative of fast-moving objects. The University of Hawaii manages this network with NASA funding, establishing new paradigms for distributed observation systems. Atlas technology demonstrated exceptional capability in early detection of 3I Atlas, providing crucial lead time for coordinated international observation campaigns before the object's closest approach. Automated detection algorithms process terabytes of nightly data, flagging suspicious objects within hours of observation for immediate follow-up by major observatories worldwide. This high-cadence survey methodology has transformed asteroid detection from periodic manual searches to continuous automated monitoring, dramatically increasing discovery rates of rare cosmic phenomena and potentially hazardous objects. Scientific theories and debates. The astrophysical community remains divided over 3I Atlas classification, with competing hypotheses attempting to reconcile observational anomalies with established physics. The hydrogen iceberg model proposes exotic solid-state hydrogen formation in deep interstellar space, though structural mechanics calculations indicate rapid sublimation rates incompatible with observed stability. Nitrogen fragment theory suggests compositions analogous to Pluto's surface materials, potentially explaining thermal signatures without conventional outgassing patterns. Dr. Alan Fitzsimmons advocates natural origin interpretations while emphasizing the critical need for comprehensive spectroscopic datasets before considering exotic explanations. Fundamental inconsistencies persist between measured acceleration vectors and detectable volatile emission rates, challenging basic cometary physics models. Statistical mechanics analysis reveals discovery probabilities for objects of this scale through random encounters effectively approach zero, forcing reconsideration of either size distribution models or visitation patterns. Advanced computer simulations struggle to reproduce observed characteristics using purely natural formation processes, suggesting either unknown physics or engineered construction. Future detection technology. The Vera C. Rubin Observatory in Chile represents next-generation astronomical detection capabilities, featuring an unprecedented 8.4-meter primary mirror integrated with a 3.2 gigapixel wide-field digital camera system. The Legacy Survey of Space and Time protocol systematically images the southern celestial hemisphere every few nights across a decade-long mission timeline. Advanced machine learning algorithms process massive data streams in real time, enabling identification of transient events, near-Earth asteroids, and faint interstellar visitors within hours of observation. Rubin's enhanced photometric sensitivity extends detection thresholds to previously inaccessible magnitude ranges, promising discovery rates of dozens of new interstellar objects annually rather than current rates of one every few years. Automated processing pipelines utilize neural networks trained on millions of astronomical images to distinguish genuine cosmic phenomena from instrumental artifacts and atmospheric interference. This technological revolution enables detection of interstellar visitors during approach phases months or years before closest approach, providing unprecedented preparation time for detailed observation campaigns. Theoretical implications. 3I Atlas detection catalyzes profound theoretical implications across astrophysics, astrobiology, and SETI research paradigms. Statistical analysis suggests these discoveries may indicate a broader population of interstellar travelers, potentially including artificial constructs deployed by advanced civilizations. Galactic archaeology models now incorporate possibilities of technological artifacts traversing between stellar systems, fundamentally altering understanding of interstellar material exchange mechanisms. The concept of automated probe networks gains credibility when considering the efficiency advantages of robotic exploration versus biological travel across cosmic distances. Advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy, systematically monitoring emerging technological species while maintaining operational security. The temporal correlation between humanity's space-age emergence and increased interstellar visitor detection rates raises intriguing questions about directed observation versus random encounters. These paradigms suggest humanity may be embedded within a complex, interconnected cosmic ecosystem where intelligence actively monitors and potentially influences emerging civilizations through strategic deployment of monitoring technologies. Future endeavors. The European Space Agency's Comet interceptor mission represents humanity's inaugural attempt at planned rendezvous with interstellar visitors, utilizing advanced trajectory prediction algorithms and rapid deployment capabilities. International coordination protocols integrate ground-based observatories with space-based assets, creating real-time global response networks optimized for comprehensive data collection during rare encounter opportunities. NASA's proposed rapid response spacecraft concepts could achieve launch readiness within months of detection, employing ion propulsion and gravitational assist maneuvers to intercept objects before solar system egress. Project Lyra, designed for Oumuamua pursuit, demonstrates technical feasibility of interstellar chase missions using current propulsion technology and precise orbital mechanics calculations. Advanced sample return architectures would enable direct laboratory analysis of interstellar materials, potentially revealing formation conditions in alien stellar environments or evidence of artificial construction techniques. Future missions deploy sophisticated analytical instruments including mass spectrometers, neutron activation systems, and high-resolution imaging arrays capable of determining composition, internal structure, and manufacturing signatures with unprecedented precision. These endeavors position humanity for transition from passive observation to active exploration of interstellar phenomena, potentially yielding definitive answers about cosmic intelligence. The technical analysis of interstellar visitors like 3I Atlas continues pushing the boundaries of aerospace engineering and astrophysics. As detection capabilities advance and propulsion technologies evolve, we approach revolutionary discoveries about advanced materials, exotic physics, and potential cosmic intelligence. Whether these objects represent breakthrough technologies or exotic natural phenomena, They're already transforming our approach to interstellar exploration. Stay connected with Stellar Tech as we decode the engineering marvels hidden in cosmic mysteries and explore humanity's technological future among the stars.
Fresh observations are now shedding new light on 3I/Atlas, the massive interstellar visitor that's been puzzling astronomers since its discovery. What started as excitement over finding our third interstellar object has transformed into something far more intriguing and honestly controversial. Recent data analysis reveals patterns that just shouldn't exist in natural objects. Orbital characteristics so precise they seem almost intentional. Professor Avi Loeb and other researchers are asking uncomfortable questions. What if 3I/Atlas isn't just a comet? What if it's something designed to study us while appearing completely natural?
Fresh observations reveal mysteries.
Recent months of intensive observation have transformed 3I/Atlas from an exciting discovery into astronomy's most controversial object since Oumuamua. Dr. Robert Warwick from the University of Hawaii, who led the discovery team, admits that new data has revealed characteristics that challenge our understanding of natural interstellar objects. The object's behavior patterns have proven increasingly difficult to explain through conventional comet models. Advanced spectroscopic analysis by the European Southern Observatory shows surface composition anomalies that don't match any known class of solar system bodies. Most puzzling is the object's thermal signature, or rather the lack thereof. Despite approaching within 0.7 AU of the Sun, 3I/Atlas shows minimal heat emission and no detectable outgassing. Dr. Michelle Bannister from the University of Canterbury noted that objects this size should be streaming gas and dust as they heat up, but we're seeing virtually nothing. The observations have split the astronomical community between those who believe there must be a natural explanation, and others who are beginning to consider more exotic possibilities. NASA's Deep Space Network continues tracking the object, but each new measurement seems to deepen rather than resolve the mystery.
The scientific debate.
The astronomical community finds itself divided over 3I/Atlas, with heated debates emerging at conferences and in scientific journals. Dr. Alan Fitzsimmons from Queen's University Belfast leads the conventional camp, arguing that extraordinary claims require extraordinary evidence, and we haven't reached that threshold yet. His team maintains that unusual properties can be explained by exotic but natural compositions, possibly involving nitrogen ice or other materials rare in our solar system. However, a growing faction of researchers questions this dismissive approach. Dr. Daryl Seligman from the University of Chicago, who previously proposed natural explanations for Oumuamua, admits that 3I/Atlas presents characteristics that are harder to reconcile with known natural processes. The debate intensified when thermal modeling by Dr. Marco Michelli from the European Space Agency revealed that the object's temperature distribution doesn't match any known natural body. Spectroscopic measurements show absorption lines that appear artificially narrow, suggesting either unknown physics or manufactured materials. Dr. Sarah Seeger from MIT cautioned against rushing to conclusions, but acknowledged that we may need to expand our definitions of what constitutes natural phenomena in interstellar space. The scientific method demands skepticism, yet the mounting anomalies are forcing astronomers to confront uncomfortable possibilities.
The artificial origin hypothesis.
Professor Abraham Loeb, former chair of Harvard's astronomy department, has emerged as the most vocal proponent of an artificial origin for 3I/Atlas. Building on his controversial Oumuamua research, Loeb argues that the object displays technological signatures that suggest intelligent design rather than natural formation. His analysis focuses on the object's perfect orbital mechanics, unusual surface properties, and lack of expected comet behavior. Loeb's calculations suggest that 3I/Atlas's trajectory shows statistical precision that would be virtually impossible to achieve naturally. The object's approach vector, timing, and encounters with multiple planets create what he calls a reconnaissance pattern consistent with systematic exploration. In his recent paper submitted to Astrophysical Journal Letters, Loeb proposes that 3I/Atlas could be a probe designed to study our solar system while maintaining the appearance of a natural comet. His hypothesis suggests that advanced civilizations might use such camouflaged objects to observe other star systems without detection. Critics argue that Loeb is making extraordinary leaps from limited data, but his mathematical analysis of the object's properties continues to gain attention from researchers who find conventional explanations increasingly inadequate for the mounting anomalies.
Unusual detection pattern.
The circumstances surrounding 3I Atlas's discovery reveal troubling patterns that suggest possible stealth capabilities. Dr. Larry Deneau from the Atlas Asteroid Survey noted that the object should have been detected 18 months earlier based on its size and trajectory, yet it remained invisible to all automated survey systems until July 2025. The delayed detection becomes even more suspicious when considering the object's approach vector from the constellation Lynx, a region of sky that multiple survey telescopes regularly monitor. Orbital reconstruction by Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory reveals that 3Y Atlas entered the outer solar system in January 2024, but somehow avoided detection despite passing through well-monitored space. The object's approach direction created additional observational challenges, as it remained positioned in areas of sky that were difficult to observe from Earth-based telescopes for extended periods. Dr. Catalina Donovan from the Linear program admitted that objects this bright should have triggered multiple detection systems, but somehow it remained hidden until practically on top of us. This pattern of avoiding detection until the last possible moment really raises questions about whether the concealment was accidental or intentional, adding weight to theories about possible artificial intelligence guiding the object's approach.
Suspicious orbital characteristics.
3I Atlas's orbital mechanics present statistical anomalies that challenge natural origin theories through their mathematical precision. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that the object's perfect alignment with the ecliptic plane has only a 0.2% probability of occurring naturally for an interstellar visitor. More striking are the object's sequential close encounters with Venus, Mars, and Jupiter, which orbital dynamicist Dr. Mattia Galeazzo from the University of Vienna determined has only a 0.005% probability of happening by chance. The precision of these encounters suggests either extraordinary coincidence or deliberate trajectory planning. 3I Atlas will pass within optimal observation range of each planet, maximizing potential data collection opportunities about their atmospheric compositions, magnetic fields, and moons. Dr. Alessandro Morbidelli from the Observatory of the Côte d'Azur noted that the trajectory looks almost designed to provide comprehensive reconnaissance of our solar system's major worlds. The object's velocity profile also shows subtle variations that correlate with planetary encounters, suggesting possible course corrections that natural objects shouldn't exhibit. Statistical analysis by Dr. Renu Malhotra from the University of Arizona concluded that the combined probability of all observed orbital characteristics occurring naturally is less than 0.001%, forcing serious consideration of artificial guidance systems.
The hidden approach strategy.
3I Atlas's approach timing demonstrates what researchers are calling strategic concealment that maximizes the object's ability to study Earth while minimizing detection opportunities. Dr. Paul Wiegert from Western University discovered that the object's perihelion passage in December 2025 coincides with Earth's position in its orbit, creating an observational blind spot that has a 7% probability of occurring randomly. During this critical period, 3I Atlas will be positioned directly behind the Sun from Earth's perspective, making detailed observation extremely difficult while allowing the object unobstructed views of our planet. Celestial mechanics expert Dr. Kleomenis Tsiganis from Aristotle University noted that this timing allows the object to study Earth's electromagnetic emissions, atmospheric composition, and artificial satellite networks without interference from ground-based observations. The approach strategy becomes more sophisticated when considering that 3Y Atlas will emerge from behind the Sun in January 2026 at optimal angles for both radio telescope detection and deep space communication. Dr. Seth Shostak from the SETI Institute acknowledged that if we were designing a reconnaissance mission to study an inhabited planet, this trajectory would be nearly optimal. The implications are unsettling. 3I Atlas appears positioned to conduct comprehensive Earth observation while maintaining plausible deniability as a natural comet.
Scientific opposition and evidence.
Despite mounting anomalies, many astronomers maintain strong skepticism about artificial origin theories for 3I/Atlas. Dr. Alan Harris from the German Aerospace Center argues that size estimates remain uncertain, and unusual properties don't automatically imply artificial construction. His team's thermal modeling suggests the object could be significantly smaller than initial estimates, potentially explaining some observed anomalies through natural processes. Dr. Vishnu Reddy from the University of Arizona emphasizes that interstellar objects should be expected to show unusual properties, since they formed in different stellar environments with unknown conditions. Counter-evidence includes spectroscopic data showing absorption features consistent with water ice and rocky materials, though critics note these signatures could be engineered camouflage. Dr. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory points out that we've only studied 3 interstellar objects, making it premature to define what constitutes normal behavior. The scientific opposition maintains that natural explanations involving exotic ices, unusual mineral compositions, or unknown formation mechanisms remain more plausible than extraterrestrial technology. Dr. Bonnie Barati from JPL advocates for continued observation rather than speculation, arguing that patience and data collection will eventually reveal natural explanations for these apparent anomalies. However, each new observation seems to strengthen rather than weaken the case for artificial origins.
Ancient origins and anomalous behavior.
Age analysis of 3I/Atlas reveals characteristics that seem to defy the natural aging process expected for interstellar objects. Dr. Grigory Fedorets from Queen's University Belfast estimates the object's age at over 7 billion years based on surface composition analysis, making it older than our solar system yet showing no signs of expected cosmic weathering. Objects drifting through interstellar space for such periods should exhibit significant cosmic ray damage, micrometeorite scarring and surface oxidation, yet 3I/Atlas appears remarkably pristine. Most puzzling is the complete absence of a comet tail despite the object's approach to within 0.7 astronomical units of the Sun. Dr. Matthew Knight from the University of Maryland noted that any object containing even trace amounts of volatiles should be outgassing visibly by now, but we're seeing nothing. Structural analysis by Dr. Jean-Baptiste Vincent from the German Aerospace Center reveals density variations that are inconsistent with typical water ice spectra, suggesting either unknown materials or artificial construction. The object's rotation period of exactly 12 hours also raises suspicions, as natural bodies typically show irregular rotation rates due to impact history and gravitational perturbations. These ancient origins combined with anomalous behavior patterns continue to challenge conventional explanations.
The stealth hypothesis.
The concept of deliberate concealment has emerged as a serious consideration among researchers studying 3I/Atlas, potentially related to dark forest theory implications for interstellar civilizations. Dr. Liu Cixin's theoretical framework, popularized in science fiction but based on real game theory, suggests that advanced civilizations might prefer stealth over open contact to avoid potential threats. Professor Avi Loeb proposes that 3I/Atlas represents what he calls archaeological reconnaissance, a method for studying planetary systems while maintaining the cover of natural phenomena. This hypothesis explains why the object exhibits just enough anomalous behavior to suggest artificiality to careful observers while maintaining plausible deniability as a natural comet. Dr. Jacob Hawk Misra from the Blue Marble Space Institute has studied the implications of such stealth strategies, noting that advanced civilizations might prefer observation over contact to minimize risks while gathering intelligence about other worlds. The stealth hypothesis suggests that 3I/Atlas could be collecting data about Earth's technological level, atmospheric composition, and artificial electromagnetic signatures while appearing to be a routine interstellar visitor. Radio telescope monitoring by Dr. Sophia Sheikh at the SETI Institute has detected no obvious artificial signals, but sophisticated probes might use communication methods undetectable by current technology or transmit data during periods when Earth-based observations are impossible.
Lessons from Oumuamua.
The scientific community's handling of Oumuamua in 2017 provides crucial context for evaluating 3I/Atlas and the importance of maintaining open-minded investigation. Dr. Robert Warwick, who discovered both objects, admits that we missed significant opportunities with Oumuamua by dismissing anomalies too quickly, rather than pursuing thorough investigation. The 2017 visitor exhibited unexplained acceleration, unusual reflectivity, and extreme elongation that were initially attributed to natural causes without adequate investigation. Professor Abraham Loeb's controversial artificial origin hypothesis for Oumuamua was largely dismissed by the astronomical establishment, yet alternative natural explanations have proven increasingly problematic under scrutiny. Dr. Daryl Seligman's hydrogen iceberg theory requires formation conditions so exotic they approach the implausible, highlighting the difficulty of finding natural explanations for truly anomalous objects. 3I/Atlas represents a second chance to properly investigate an interstellar visitor with advanced instruments and sufficient observation time. Dr. Thomas Zurbuchen, former NASA Associate Administrator, emphasized that extraordinary phenomena deserve extraordinary investigation, not extraordinary dismissal. The lesson from Oumuamua is clear. When faced with genuinely anomalous objects, the scientific community must resist the temptation to force natural explanations and instead pursue comprehensive investigation that considers all possibilities, including those that challenge our current understanding of what's possible in the universe. 3I/Atlas continues its journey through our solar system, carrying secrets that may fundamentally challenge our understanding of what travels between the stars. Whether it's an exotic natural phenomenon or something more extraordinary, this mysterious visitor has already forced astronomers to confront uncomfortable questions about the universe around us. The patterns are too precise, the timing too convenient, and the behavior too strange to dismiss easily. Subscribe to Stellar Tech for more investigations into cosmic mysteries that blur the line between natural phenomena and something far more intriguing. What if I told you that in 2017, something from another star system visited our solar system, and one of Harvard's top scientists believes it might have been sending us a message? Oumuamua, the first confirmed interstellar visitor, has sparked the most controversial debate in modern astronomy. When Joe Rogan sat down with physicist Avi Loeb, the conversation revealed shocking theories that challenge everything we thought we knew about our cosmic neighborhood. Today, we're diving deep into the mystery that has scientists questioning whether we've already encountered alien technology.
The discovery that changed everything.
October 19, 2017, marked a historic moment that most people completely missed. On that day, astronomers at the Pan-STARRS telescope in Hawaii detected something that shouldn't exist, an object moving through our solar system at impossible speeds, following a trajectory that proved it came from another star system. Named Oumuamua, meaning messenger from afar arriving first in Hawaiian, this mysterious visitor was unlike anything scientists had ever encountered. The object was traveling at 196,000 miles per hour, far too fast to be captured by our sun's gravity. Its hyperbolic trajectory confirmed what seemed impossible. We were witnessing humanity's first confirmed interstellar visitor. What made this discovery truly extraordinary wasn't just its origin but its timing. Astronomers estimate that interstellar objects like Oumuamua pass through our solar system about once per year, but they're typically too faint and fast to detect. Only recently had our telescopes become powerful enough to spot such visitors. The fact that we caught this one suggested either incredible luck or that these objects might be more common than previously thought. Within days of its discovery, Oumuamua would reveal characteristics that would divide the scientific community and spark debates that continue today.
An object unlike anything we've seen.
The more scientists studied Oumuamua, the stranger it became. This wasn't just another space rock. It was something that defied every category astronomers had for celestial objects. The object's shape was the first major anomaly. Based on how its brightness changed as it tumbled through space, scientists calculated that Oumuamua was extremely elongated, roughly 10 times longer than it was wide. To put this in perspective, imagine a cigar that's 1,300 feet long but only 130 feet wide. No asteroid or comet in our solar system has ever been observed with such an extreme aspect ratio. Even more puzzling was its behavior. As Oumuamua rotated every 7.3 hours, its brightness varied by a factor of 10, the most dramatic brightness variation ever recorded for a natural space object. This suggested either an incredibly unusual shape or surface properties unlike anything in our cosmic neighborhood. The object's reddish color, similar to objects in the outer solar system, indicated it had been wandering through interstellar space for hundreds of millions of years, its surface reddened by cosmic radiation. Yet despite this ancient journey, Oumuamua showed no signs of the dust or gas emissions typical of comets when they approach the sun.
The acceleration mystery that baffled scientists.
Just when astronomers thought they understood Oumuamua, the object delivered its most shocking surprise. It was accelerating away from the sun in a way that gravity alone couldn't explain. This non-gravitational acceleration was subtle but unmistakable. As Oumuamua sped away from our solar system, it was moving faster than it should have been based purely on gravitational calculations. For comets, this kind of acceleration is normal. Ice vaporizing from their surface creates a rocket-like effect. But Oumuamua showed absolutely no signs of cometary activity. The acceleration was consistent and measurable, ruling out random forces or measurement errors. Something was pushing Oumuamua, but what? Traditional explanations fell short. The object was too small for solar radiation pressure to account for the observed acceleration, and it lacked the outgassing that typically propels comets. This mysterious acceleration became the smoking gun that would fuel the most controversial theory in modern astronomy. If natural explanations couldn't account for Oumuamua's behavior, what could? The answer would come from an unexpected source, Harvard's Department of Astronomy, where one physicist was willing to consider possibilities that others dismissed as impossible. The stage was set for a scientific revolution that would challenge our understanding of our place in the universe.
Avi Loeb's revolutionary theory shakes science.
When Harvard physicist Avi Loeb appeared on Joe Rogan's podcast, he dropped a bombshell that sent shockwaves through the scientific community. Oumuamua might be artificial technology from an alien civilization. Loeb, former chair of Harvard's astronomy department, wasn't some fringe theorist. He was a respected scientist with hundreds of published papers, who had simply followed the evidence to its logical conclusion. Just like Sherlock Holmes, I follow the evidence, trying to find the solution. The physicist's theory centered on one key insight. Oumuamua's unusual properties perfectly matched what engineers would design for an interstellar light sail. Its extreme thinness would minimize damage from interstellar dust, while its flat geometry would maximize surface area for solar radiation pressure. Exactly what would propel a light sail through space? Loeb's calculations showed that solar radiation pressure could indeed account for Oumuamua's mysterious acceleration, but only if the object was incredibly thin, like a sheet of paper tumbling through space. This wasn't just speculation, it was based on rigorous physics and observations that other natural explanations couldn't adequately address. The scientific establishment's reaction was swift and harsh, but Loeb stood firm in his assessment.
The light sail theory that changes everything.
The concept that Oumuamua could be an alien light sail isn't science fiction, it's cutting-edge physics that we're already developing here on Earth. Light sails work on a simple principle. Photons from stars carry momentum that can push extremely thin reflective surfaces. Just as wind pushes a ship's sail, starlight can propel a spacecraft equipped with a large, lightweight sail. The technology is so promising that organizations like Breakthrough Starshot are developing light sail probes to reach nearby star systems. Oumuamua's behavior perfectly matched what scientists would expect from a light sail. Its acceleration was consistent with solar radiation pressure acting on a thin, flat object. The lack of outgassing made sense because artificial objects wouldn't contain volatile materials that vaporize near the sun. Even its tumbling motion resembled how a damaged or derelict light sail might behave after millions of years in space. Maybe it was just alien craft technology that unintentionally lost itself, like space junk. Loeb suggested, making the theory seem less threatening and more plausible.
The search for alien signals begins.
The possibility that Oumuamua might be artificial technology triggered the most intensive search for alien signals in modern history. Breakthrough. Listen, the world's most comprehensive SETI program immediately turned the massive Green Bank telescope toward Oumuamua. If the object was indeed artificial, it might be transmitting signals, either intentionally or as electromagnetic leakage from its systems. The search was unprecedented in its scope and sensitivity. Over multiple observation sessions, the telescope scanned billions of radio frequencies, recording a staggering 90 terabytes of data, enough to fill 23 high-end computers. The observations covered different phases of Oumuamua's rotation, ensuring that any potential signals from different parts of the object would be detected. The sensitivity was remarkable. At Oumuamua's distance, the telescope could have detected a signal as weak as a cell phone transmission. If alien technology was aboard this mysterious visitor, we would have heard it. The results were both disappointing and reassuring. No artificial signals were detected from Oumuamua. The object remained silent as it tumbled through space, offering no direct evidence of alien technology. However, the absence of signals didn't disprove the artificial hypothesis. A derelict piece of technology wouldn't necessarily be transmitting.
Why natural explanations fall short.
The scientific community's resistance to Loeb's alien hypothesis led to, well, increasingly creative attempts to explain Oumuamua through natural processes, but each explanation just seemed to create new problems. One theory suggested that Oumuamua was a hydrogen iceberg, basically a chunk of solid hydrogen that would sublimate near the sun, causing the observed acceleration. But, solid hydrogen couldn't actually survive the millions of years needed for interstellar travel, and the object didn't show any of the expected hydrogen emissions. Another proposal claimed Oumuamua was a fragment of a disrupted comet, but this idea couldn't account for its extreme elongation or the lack of any cometary activity. Some scientists even suggested it was a dust bunny, meaning a loosely bound collection of particles, but an object like that would have been torn apart by tidal forces during its close approach to the sun. The most recent theory proposed that Oumuamua was made of nitrogen ice, kind of like Pluto's surface. While this could maybe explain some of the observations, it would require the object to have originated from a Pluto-like world in another star system, which is, honestly, itself a pretty extraordinary claim. So, each natural explanation required increasingly exotic conditions or materials, leading some scientists to start questioning whether the artificial hypothesis might actually be the simpler explanation. The implications of alien technology. If Oumuamua truly represents alien technology, the implications for humanity are, honestly, staggering, and fundamentally change our understanding of our place in the universe. The object's properties suggest it wasn't sent to spy on Earth or, make contact. Its trajectory showed no signs of course corrections toward our planet, and it was already leaving the solar system when we discovered it. This supports Loeb's theory that we encountered cosmic debris, the equivalent of finding a piece of alien trash just floating through space. Strangely enough, this scenario might actually be more significant than active alien contact. It suggests that technological civilizations are common enough that their artifacts regularly drift through the galaxy. If Oumuamua is artificial, it implies that advanced civilizations have been building interstellar technology for, well, millions of years, leaving a trail of debris in their wake. The discovery would also validate humanity's own technological trajectory. We're developing light sail technology for interstellar exploration, which suggests that this approach represents a natural evolutionary step for spacefaring civilizations. Oumuamua might be showing us our own future, a time when human-built light sails will traverse the galaxy, potentially becoming mysterious visitors to other star systems.
The race against time and distance.
One of the most frustrating aspects of the Oumuamua mystery was just how quickly the opportunity to study it disappeared, highlighting the challenges of investigating interstellar visitors. By the time scientists realized Oumuamua's true significance, it was already racing away from the sun at, honestly, incredible speed. The object was moving so fast that no existing spacecraft could catch up to it for a closer look. Even our most powerful rockets would have taken decades to reach Oumuamua, and by then it would be way too far away to study effectively. This time, pressure forced astronomers to make critical observations with ground-based telescopes while the object was still detectable. Every day that passed meant Oumuamua was getting fainter and harder to observe. The window for detailed study lasted only a few months before the object became too distant for meaningful analysis. The experience taught scientists some valuable lessons about preparing for future interstellar visitors. New detection systems are being developed to spot such objects earlier, giving researchers more time to study them. Space agencies are also considering rapid response missions that could be launched quickly to intercept future visitors before they escape our solar system.
What Oumuamua means for the future.
Oumuamua's brief visit has, without a doubt, fundamentally changed how we think about interstellar space and our search for extraterrestrial intelligence, regardless of whether it was natural or artificial. The object proved that interstellar visitors are detectable with current technology, opening a whole new field of astronomy. Scientists now know what to look for and have developed protocols for studying future visitors more effectively. The recent discovery of additional interstellar objects, including Comet 2I Borisov and the newly detected 3I Atlas, shows that Oumuamua wasn't a unique event. If Oumuamua was indeed artificial, it suggests that the galaxy might be filled with technological artifacts from ancient civilizations. This archaeology of the galaxy approach to SETI represents a new way of searching for evidence of alien intelligence, not through radio signals, but through physical artifacts drifting through space. The controversy surrounding Oumuamua has also highlighted the importance of keeping an open mind in science. Loeb's willingness to consider unconventional explanations, despite professional criticism, really demonstrates the value of following evidence wherever it leads. As we continue to develop our own interstellar technology, Oumuamua serves as a reminder that we might not be alone in this cosmic endeavor. From its mysterious acceleration to its impossible shape, Oumuamua challenged everything we thought we knew about our cosmic neighborhood. Whether it was a natural phenomenon or humanity's first encounter with alien technology, this interstellar visitor opened our eyes to possibilities we never imagined. As Joe Rogan and Avi Loeb showed us, sometimes the most extraordinary explanations deserve serious consideration. The truth about Oumuamua may remain a mystery, but its impact on science and our understanding of the universe will last forever. Thanks for watching Stellar Tech, and don't forget to subscribe for more cosmic mysteries.